So today the second talk will be about analytic combinatorics and will be given by Mark Wilson from New Zealand, but who might be in the US right now.
Yeah, I'm hiding in Massachusetts at the moment.
And he's going to talk about higher dimensional lattice walks.
So thank you very much. I don't work in algebraic combinatorics per se, but it's been very interesting to hear such good talks and meet some interesting people. And I think there is definitely room for more collaboration. Hope to convince you of that. This is joint work with my excellent co-author, Stephen Melczer, on a paper that's recently been published, as you can see. So I'm going to start off with a question. Imagine you're in the lattice, in the plane, the integer lattice, and start from the origin, and you can go to 3 of your 8 possible neighbors. You can go down, you can go up to the left and up to the right, and that's all you're allowed to do. You can move around repeatedly subject to those constraints as long as you don't leave the first quadrant. So it's like some kind of generalized gambler's ruin setup. Or you could do it with the steps in there which are completely reversed. So down, I got it wrong again, down to the left, down to the right, and up. So the inverse of the previous steps. So the interesting thing is that conjectured based on a lot of evidence, you have these asymptotic formulas for the numbers of such walks, and they're very different from each other. Different exponential rate, different polynomial corrections, and one of them is periodic and the other one is not. So this requires an explanation. And these sorts of problems have been studied a lot. There's a lot of papers over the last 10 years or so on walks confined to cones, or such as the first quadrant, for example. So the big picture for today is we're just going to look at these walks on the integer lattice, and we're only going to allow these short steps. So you can only go to your nearest neighbor. There are certain constraints that could be considered. We're mostly going to look today at the non-negative orthant, but you can have plenty of other constraints as well. We're going to keep track of the endpoint. We're going to try and enumerate these. We can look at the endpoint RS, let's say, in the two-dimensional case, and we also have this variable t, which is keeping track of the length, the number of steps. If we forget about the endpoints, then we're just looking at the number of steps. We're looking at these numbers fn, and in particular, we want to look at the asymptotics of those. So that is the big picture. I want to now just have a brief interlude of the kind of generating functions you might be expecting. Some of the most common classes of generating functions that come up are obviously rational functions. We're going to be doing things in more than one variable, as you saw there, just to remember that. But rational generating functions are obviously fairly well known. Algebraic functions, we all know what those are. D-finite functions are those that satisfy a linear ODE with polynomial coefficients, or equivalently, the coefficients themselves satisfy a linear recurrence with polynomial coefficients. Worse than that, I guess, are things which are differentially algebraic, so they satisfy a nonlinear differential equation, and it could be even worse than that. In the realm of lattice walks, we get all of these classes arising, I believe, or at least most of them. Certainly the rational functions, that's what you get typically in such a problem when you have no restriction on the walks. If you confine to a half space, it's been known for quite a long time that you tend to get algebraic functions. We will see later that D-finite functions arise when you increase the number of constraints there. So we're now confined to a quadrant, and quite easily you can run into poorly understood classes and not D-finite. So I want to now talk about some previous work on the general problem. So the seminal paper, I'd say, is Bostan and Mishna, where they reduce the 255 classes, that's 2 to the 8 minus 1, of walks a priori by various symmetries and reducing to previous work. They showed there's still 79 cases that need to be discussed. They introduced a symmetry group, which I talk about a bit later, and they showed that it's finite in 23 cases, and they used the finiteness to show something nice about the generating function using methods that we'll again talk about a little bit. So there were 22 of those 23 cases, and one of them, the method failed. That was the Gessel walks, which was finally dealt with by heroic efforts soon after. It's algebraic, but the minimal polynomial is so large that you would never want to look at it. They're talking gigabytes to store these things. They have large degree and large coefficients. The other cases, at this stage, there doesn't seem any easy way to attack them, although it's not out of the question, I think. So for now, we're going to concentrate on the quote easy cases, which are certainly hard enough. So of those easy cases, there were 23, all of those cases had asymptotics conjectured based on clever computer algebra techniques and deep analysis of one variable generating functions. But they were not proved. 4 of them were dealt with. We'll see them at the end. So there's 19 left. Those were, the answers were expressed in some alternate form, but still not in a way that enabled us to actually solve the problem we're interested in. And then Melczer and Mishna did the 4 easiest remaining cases using the kind of methodology I'm going to talk about today. But there were still 15 left, and basically the upshot of this paper is that all of those have been dealt with in a fairly unified manner. So we have finally solved at least a chunk of the quadrant walks, right? So terminology, basic multi-index notation, so I don't have to write long products. We're looking at multivariate sequences. So in the quadrant case, it's trivariate, I guess, the way we had written it out. We were keeping track of the endpoints, for example, and the length. We've got the generating function, standard object. Now I'm going to assume here that the generating function that comes up is rational in several variables. We'll see why that's good enough for us later on. It also enables us to do computational commutative algebra, so it's quite handy. But the kind of methods I'll be talking about very soon go way, way beyond that. It's just for simplicity. The so-called singular variety is just the set of poles. It's the zeros of the denominator. And it turns out that things become quite hard when you get outside the combinatorial case. And unfortunately, combinatorial problems sometimes lead to non-combinatorial problems, which I may have time to talk about. So I'm going to restrict the discussion right now to the case where all the coefficients are non-negative. So that hopefully should be convincing that we can do that, but you'll see actually that maybe that you can't always do that, but we'll plow ahead. So the reason why we worked on this project is that we knew that there's been something called analytic combinatorics in several variables, which Robin Pimentel and I started and many other people have worked on. And it's ended up in a book and various papers. We knew that we had a chance of dealing with this problem. And so I want to give you an idea now of sort of the basic results that were already in our mind before we started looking at this. So the idea is you've got a generating function. It's, let's say it's rational. and it's encoding some multivariate sequence. So you need to first work out what direction you're going to look at asymptotics in. That's not something you have to think about in one variable, because you're going to infinity and there's only really one way for n to go to infinity. Here, of course, we could be going out in many different ways. So let's imagine we're going along a specific ray, and we just go out there. Now, it turns out that in order to produce asymptotics in that direction, you first need to calculate a variety which what we call critical points. So they're defined, it's given by algebraic polynomial equations, right? And we'll see that, hopefully. That's a step that you don't get in the one variable case. Then we have a step which is kind of similar to the one variable case, where if you do generating function analysis, you need to look at the singularities of the generating function. That gives you a lot of information, but you only really need to look usually at the ones that are closest to the origin. And this is the kind of idea here, although there's more to it. The more geometry and topology intervene in higher dimensions, but this is basically the idea. So we can cut down usually to a smaller set of points which are actually relevant, and if you're lucky, there's just a single point. It's usually finite. Now, again, if things go well, for each contributing point, we can actually calculate a full asymptotic expansion contributed by that point, and that's usually enough to solve the original problem. Now, it depends on the local geometry of the singular variety. Again, in one variable, there is not much interesting geometry because the zeros of the denominator are isolated points, and that's all you can say. But in two or more dimensions, you have non-trivial geometry there locally. If everything goes well, which it has in many cases, then we can write down a full asymptotic expansion. And one of the key things I want to point out is that it's uniform. So for example, suppose you had a bivariate sequence and you had the 1000, 1000 entry, something on the main diagonal. That can be calculated quite easily sometimes by other methods, such as the diagonal method, let's say. You'll find that in one of Richard Stanley's books, among many others. It doesn't work very well if you wanted, for example, to understand what the 1002,999 entry would look like. And if you want some kind of uniform approximation, the only method that I know that works is the one that we have produced, which is based on multivariable complex analysis. So let me give you an idea of the kind of formulas we knew that we had. Don't worry too much about every detail in here because there's a lot of formulas, but basically you can get an asymptotic contribution to add a contributing critical point, which is not that bad. It can be described in terms of geometric data, which is what I'm trying to do there. The key thing you need to realize is that everything in that formula can be calculated by just polynomial algebra, as it turns out, and just involving derivatives of up to second order, in fact. This is the nicest case. Where does it come from? It comes from transferring to the realm of harmonic analysis and doing some work saddle point integrals. Since we're virtually in Sweden, I thought it was important to show you the next slide, which is just an idea of the kind of formula we might be applying. You don't need to understand all the details, but we reduce to formulas of this sort. So this is in Lars Hermander's book, The Analysis of Linear Partial Differential Operators, Volume 1. And you can see he has an explicit formula, which is quite amazing, which gives an asymptotic expansion of an oscillatory integral in terms of nasty but potentially doable calculations involving explicit operators. Doing that with, say, Sage in a specific example is possible. We've got implementations which work reasonably in many cases. Doing it by hand for a general type of problem, as we had to do here, is another thing entirely. So that's where I ended up spending many weeks. calculating by hand. So the outline of the approach is that it turns out that we can actually get more general results. We can get weighted walks, which allows us to give positive weights to steps so that we could think about probability and random walks, for example. We express the values that we want as diagonal coefficients, so on the leading diagonal of some much larger dimensional object, but it's rational. There's a trade-off between dimension and sort of functional form niceness. If you insist on being in one variable, you tend to get nasty looking generating functions. If you try and interpret them as diagonals of higher dimensional things, you can often get away with rational functions. So that's the big principle there. We used the standard theory that we had already developed to try to extract asymptotics. We had some difficulties. One is that we can't do every possible case of singularities, obviously, there are a lot of them. It turned out in this case, however, that it was doable, except for the fact that, interestingly, the generating function that we lifted up to in the larger number of dimensions had some negative coefficients. There were no negative coefficients on the leading diagonal because those were counting things. Those were the original numbers of walks. But it's not unique, the way of doing this. And the standard way that we did it gave negative stuff, which tends to lead to major technical difficulties. In terms of identifying, the big problem is it's very hard to identify what the contributing points are. Instead of using relatively simple convex analysis, you start getting into computational Morse theory and things that I would rather avoid. The other difficulty is that in this formula we had here, back here, you see you've got G, the numerator of the rational function. If that's 0, then that's not telling you very much. It tells you haven't captured the correct asymptotic order there. And so it turns out, unfortunately, that we're in that case. And so the higher order terms are really unpleasant to write out. So we thought hard about difficulty 1, and we were close to solving it, I think, maybe, but it was not at all convincing. So we tried again, and we came up with a general purpose method, which I intend to use again if I'm allowed, which is to ask Mireille for the answer. Right? Now, she spent 24 hours maximum and sent back a thing basically saying, if you adjust your generating function like this, you still have the same diagonal, but all the terms are positive. That made things very much easier. It was a little bit nastier looking than our original one, but it was still doable. So again, I recommend that method to you. Solution 2 was just unpleasant and had to be ground out. So I'll show you the results in a minute. I just want to show you.
Mark, is this a good place to interrupt for a moment?
Yes, yes.
There was a question about the actual statement, if you can go back before the outline of approach and just clarify, what is lambda in that formula? Is that a indeterminate, or you're thinking of some?
Yeah, it's for some lambda. Yeah.
Okay.
There exists some lambda for which that is the case. Yeah. So you get a system of equations. You can typically, it's the right size for the number of variables, and you can solve it. And if you typically you get a zero-dimensional or finite zero-dimensional variety, just a finite set of solutions. And typical cases, of course, interesting combinatorial problems tend to throw up non-generic or non-typical behavior, but this is still good enough to solve many things. Shall I go on?
Yes, thank you. I think that answers Todorus's question.
Great. So Melczer and Mishna, we're not looking at all possible walks. It's complicated. They looked at the case in general dimension where the step set is completely symmetric. So if you step forward in one direction, you step back in the same direction. If you have a forward step in one direction, then in your set you must also have a backward step in that same direction, and everything is completely symmetric. So that's as symmetric as you could possibly be. We analyze the case where you have almost as much symmetry as you'd expect. You drop one axis of symmetry and everything else works. Now, why did we do that? One reason is that if you go further than that, then you in general, you're not going to get a D-finite solution. So the specific methodology we're using here clearly will fail. It doesn't mean that it couldn't be adapted, but it's definitely going to be much harder. Another reason is that that was enough for us to solve the two-dimensional problem that we talked about at the beginning. So what we're going to do is we're going to write out this generating function of the step set. And we write it out, it's basically, we think about ZD, D is the index of the dimension where you don't have the symmetry. If we did, then A would be equal to B in that formula. And A and B depend on the other variables, and so does Q. And basically, we just single out that one variable, and since they're only stepping plus or minus 1 in that, we're only going to our nearest neighbors like that, you only get powers of plus or minus 1 or 0 involved there. Now, you then define what's called the drift, which is basically in that dimension, the difference between the weight of the positive and the negative steps. Which gives you an idea. If you had a random walk, you think about it gradually drifting in one direction or the other.
So can I interrupt again with another
Yes.
question? I've never had asked. How do you choose which axes to keep the symmetry of? On your second bullet point there.
We're not choosing them. We're just assuming that they're given, and I'm reordering the variables to call it D.
Okay.
Yeah. So I'm calling D the non-symmetric, ZD the non-symmetric axis. But yeah, we're just assuming that you're given a case where your step set is given and it turns out to have that much symmetry. Okay?
Okay.
So I'm going to very briefly go through the next part. Most of the methodology I showed you before about asymptotics assumes that the generating function is given, and then we just analyze it. But of course, you do have to derive the generating function as well in many situations. Here, there's a reasonably standard methodology that Bostan and Mishna had pioneered, and it roughly goes like this. So you have this kernel method, which is a very powerful tool that's been used in lots of combinatorial enumeration problems. In this case, it leads to, by doing a relatively simple recursion on these steps, just look at the last step, for example, or the first step and recurse on that, you end up with this nice equation here where the LKs are Laurent polynomials, I believe, yeah. And now the symmetry group G that I talked about before, it's generated by, in the symmetric case, you just invert the variable multiplicatively. And in the non-symmetric one, you do something slightly different. In fact, you're doing the same thing in every variable. It's just that it simplifies in the symmetric case to have a nicer formula. Now, if you apply the group elements to that equation and then sum in a carefully controlled manner, it turns out you almost fix one side and you kill off a lot of stuff on the right side. And that enables you to solve by saying, well, what we want is a power series, so we only want positive coefficients. So we take the positive part of a Laurent series. And then it's only a small step from there to express the positive part of a series as a diagonal. You basically make a monomial transformation of your variables. It's a fairly straightforward thing. So the big picture is that we get this generating function. So it's explicit, it's a little ugly, but everything is written in terms of the original data on that step set. You have your enumerator S, and that A, B, and Q can easily be derived from that with no work at all. Okay? Completely automatic. And so you have this thing with 3 factors in the denominator, H, and the leading diagonal of that D+1 dimensional generating function encodes the very numbers that we're interested in, which is kind of a nice fact. But now we have to go ahead and analyze it. So it turns out that in the case with positive drift, it's really just off the shelf. We just looked up what we'd already done, translated it all into this language, and it just works. So that was great. The exponential rate, S of 1 is the total weight of the step set. You've got a polynomial correction there, you've got a power of n, and then you've got a big constant there, which you can easily compute. Okay, it's algorithmic and simple. So that was nice. So at that stage we were happy. However, it gets more interesting. So the negative drift case, it's much more interesting. So here, it turns out that in the positive drift case, the contributing critical point turned out to be what's called a multiple point. It's basically locally, the singular variety is an intersection of smooth sheets. Here, it's actually a smooth point, so it should be nicer, but it's located in a slightly unusual place, not where we'd necessarily expect it. Excuse me. And there's also periodicity. There's two cases here, which is kind of hard to understand straight away. But you do remember we had periodicity earlier on.
Another good question here, which is, are you sure B1 is not 0?
Oh yeah, okay. So yeah, that is a non-degeneracy assumption you have to make, yeah. Otherwise, you end up with steps that don't move at all in one direction. So you're reducing the dimension, essentially. It's a degenerate problem. We're looking at things that are of full dimension here. So it's a genuine two-dimensional walk, for example, rather than a one-dimensional walk that just happens not to go into the second dimension. So that's a good point. So if you have a genuinely d-dimensional walk, you will never have a problem with something being 0 where it shouldn't be. Here's an example of what might happen. In 2 dimensions, you've got your standard cardinal compass points, compass directions, and you have weights on 2 of them and not on the others, just for simplicity, because the formulas get big. And you can see there's different cases depending on the weights, whether you have positive or negative drift or a 0 drift, which I haven't talked about yet. And you get different exponential rates and different polynomial corrections, and you can see everything working there. So it's kind of nice problem. Now here's the table which shows these. So remember there were 23 cases that I said were quote interesting. Here are the final answers for the asymptotics we wanted. You can see they get quite complicated down the bottom right there, some of the formulas. You'll see some patterns there. If you look in the middle column, you'll see 3 to the n, 4 to the n, 5 to the n. It's just the step set, size of the step set to the n. These are the unweighted walks we're looking at. You'll also notice that the second to last one on the middle column doesn't have the kind of symmetry I've talked about. There were a few cases where we had to do them by hand using the same ACSV methodology, just case by case. But we did those. But most of them come in these families. And on the left column is the first 4 are the simplest ones. The last 4 are the hard ones that were done by different methods because they have generating functions that are algebraic, not only d-finite, but actually algebraic. They were done by Bostan and Kauers and that kind of sub-community. I'll say a little bit more if I have time. You can see there that there's periodicity as well, and that's written in those constants A, N, B, and C, N. So what are some possible extensions? Well, you can actually, if you constrain them to return to the axis or to the origin, instead of just staying inside the first orthant, you get small modifications to the analysis, which enable us by a unified method to solve it. So for example, here's a fraction of the table you would get. These numbers are delta n and epsilon n are just parity related number, like maybe 1 if maybe it's the Kronecker delta, n equals n, delta's 1 if n is even and 0 if it's odd, but that kind of thing for the periodicity. It's actually instructive to study this if you have time and see the difference between this and the the walks that are not constrained to return in that way. But the point I want to mention is that it's just fairly powerful general methodology which enables you to do a lot of related questions. Walks and vial chambers, the highly symmetric case on the top left of this column, top left of this table, is an example of that, of one particular type of vial chamber walk. There's, I think, Gessel and Zeilberger derived nice generating function. The analysis is a little messier, but the same kind of methods should work. There's been a little bit of work done on that, but not much. So I think that's something that could easily be also an obvious place to work. Zero drift is tricky. I did a lot of work on some case and I thought I'd finished it. Then I realized that that case had subcases, which also had subcases, and it was kind of obvious when you thought about it. So it was too difficult to work out in full generality, but we have done something. The algebraic generating functions I mentioned before that were done by other people. In theory, our methodology would work. It's obvious from the coefficients, like the 3/4 and the 2/3 in the bottom left of the table, that the exponents of n, I mean, it's obvious that something quite different is happening geometrically there. What you're going to get quite different singularities. I have actually looked at one of those, and it's ugly, but it's a great challenge for us to try and extend the general theory that we've got. And there are some cases where walks that are not just nearest neighbor might actually be doable. I had a look at this week at a few papers that were somewhat related to what we've been doing and to the lattice path literature, and it seems like there are some cases where you can derive reasonable generating functions that can be dealt with. Here are the references. They're clickable when these slides are finally available to everyone, which should be by the end of today. I encourage you to have a look through there. Here's just an example of the two-dimensional case where you didn't have symmetry. It was just an algebraic trick to rewrite it as a sum of two things that look nice, and used our methods. And that's all I have to say. Thank you very much.
Okay, thank you, Mark, for this really nice talk, this work in analytic combinatorics. So I let Sarah handle the questions.
Yeah, very nice talk. We had a few questions going on in the chat that I think I interrupted to get all of those. And I'm looking for a raised hand. I see Arvin has a hand, so let me unmute you, Arvin. Go ahead.
No, sorry. I was trying to clap. Sorry.
Oh, well, that's good too. Okay, let me see if there's anything else. Well, I had a question. Maybe I could ask my own first. I haven't really thought too much about using the variety structure on the denominator of a generating function to get information, enumerative information. So how much do we know about that actually? What if, you know, there's all this in algebraic geometry, there's a lot of theory of the classification of singularities. If you have a rational singularity versus other types, log canonical singularity, does that matter in terms of the enumeration?
Well, my limited understanding is that, yeah, there are theorems. Making them computationally effective is a big issue. Let me say that, for example, there are plenty of interesting algebraic generating functions which don't fall directly into what I've been talking about here, since I was just talking about rational ones. There are also ways like resolution of singularities that will kind of lift to a higher dimensional space where higher number of variables, and you get that trade-off I talked about before. You go up to a nicer function, a rational one. Making that effective is basically one of the things we want to do next. All right. So, I mean, you can see we need very precise information here to be able to calculate these asymptotics. You need to know everything about how are you resolving the singularity. So there are certainly small cases where I can do it by hand, but ultimately we're aiming to produce software, and we're trying to do it as algorithmically as possible. You know, there is an AMS mathematics research community which is sort of on hold for this summer, but will probably happen virtually. There's an AIM workshop as well we're having next year. And we're looking at extensions of this sort to try and, so far what I've showed here is pretty much, even though there was quite a lot of work, it was a direct application in the end of the two simplest types of geometries that you're looking at. And we want to push further than that. So that's the big picture, yeah. We're still looking at extra development.
Thanks, very interesting. All right, well, if you would unshare your screen, we can see the silently applauding people.
Thank you. If you have an interesting rational generating function, send it to me. That's the takeaway from this talk.